Riemann sums. Okay. It sounds fancy. There is some technical stuff that we'll get to later, especially Friday. But all we're going to do today is add areas of rectangles. All right, so help me out, geometry all-stars and elementary school math. What's the area of a rectangle? Oh, you guys are awesome. Length times width. Sometimes we phrase it as base times height. Base times height is maybe a better way to think of it for what we'll do today. But base times height. And we're going to add them up. So we'll get more than one. We'll get 2 or 4 or 8 or however many. And add them up. We'll also add, so this gets a little bit trickier, area of trapezoids. I know, you may not remember the area of a trapezoid. Let's draw a trapezoid like that, which is not how you normally think of drawing a trapezoid, but it's how we'll draw our trapezoids. Where that's the base, and we've got 2 different heights now. So it's got 1 base and 2 heights. Do you know how to find the area of a trapezoid? What's that, Ben? I think you said it. Okay, you're in the ballpark. There's a 1/2. Basically, the way to remember it is it's base times, now there's 2 heights. Which one should I use? I don't know. How about the average height? This is how I remember it rather than remembering a formula. It's still base times height, but it's more like the average height. And the average height would be h1 plus h2 over 2.
Could you not do like base times h1 and then base times h2 minus h1 like over 2? Or is that just complicated?
Yeah, that what you said is absolutely right. Like Jason's saying, well, why don't I split this up into a rectangle and a triangle? And what you said, I think, was right, and I bet it would eventually come down to this.
It's just, okay, that's
In fact, I know it would, because you would have 1 BH1 minus half a BH1 would get you to the half BH1. What you said was right. But for our purposes, it's going to be much easier if you remember it this way. Much easier if you remember it this way. Okay, so we're about to get into the technical stuff, but I don't want you to lose sight of the fact that all we're doing today is adding rectangles, adding trapezoids. So when you see Riemann sums, it sounds fancy, German guy, like there's lots of complicated things to come, but today, add up the rectangles or add up the trapezoids. And it will be very clear when you should use rectangles versus trapezoids. In fact, if you just look down the page there's 4 pictures. And which one of the 4 do you think you use a trapezoid on? The one that says trapezoidal sum. That sounds like you should use a trapezoid. Okay, so let's get into the details here. But again, don't lose sight of the big picture. All we're doing is adding up rectangles. We want to find the area under a curve between x equals a and x equals b. By the way, this is the same thing we did like first day of school long ago when we lined out the rectangles of toilet paper and added them up. That's what we're doing today. We're finally there. Riemann sum approximations use rectangles to approximate the area under the curve. Right? Because those rectangles of toilet paper there, like they're pretty close. That's probably a reasonable approximation of the yellow area, but it's not exact. Like because some of them are over, a few of them are under. Like it's close. It's an approximation. We're going to use rectangles, basically because we know how to find the area of a rectangle very easily. It's like, well, why didn't we pick something else? Like, well, rectangles are easy. Riemann sums are named after the guy who, figured this out. It's like he gets credit for adding up rectangles? Like, yes he does. German mathematician Bernhard Riemann. I didn't realize, just until now I realized he didn't make it very long. Right? I mean, 40 years old, so I say 1800. But still, they lived past 40, right? All right, back to, we can draw rectangles. Okay, so here's where we have to be a little bit careful. We can draw rectangles using the left side of each rectangle, or the right side, or the midpoint. So kind of going big picture here, and then we'll get into the details. Your three rectangle options are, you can use the left height, the right height, or the middle. Left height, the right height, or the middle height. In fact, let's divide this into four. Let's divide it into four equal, like sub-intervals here. My widths aren't perfect there, but you get the idea. In fact, let's do that on all four pictures. It will be kind of comparing apples to apples here. So I'm going to divide each region into four sub-intervals on all four pics. So kind of cut it in half and cut it in half again. Draw straight lines. I don't know how straight mine are, but there's the. So I've got each of my areas divided into four sub-areas. Okay, the first one is we can draw rectangles using the left side of each rectangle as the height of the rectangle. I'm going to say the left side of each region. To me, that makes more sense because I got four regions now. And if I want to use the left-hand height, then I'll come to the left, and there's my first rectangle, because I use the height on the left-hand side of the region. And my second rectangle, again, use the left-hand height. This one would be bigger than the actual area, but that's all right. Again, coming from the left-hand height of the rectangle. That third one's pretty close to a reasonable height or a reasonable area. Last one, using the left-hand height. That one's definitely under, but it's an approximation, so we're not worried about over or under just yet. Those are my left-hand heights. That's my left-hand rectangles, left-sided rectangles. And when we ask you to do a left-sided rectangle, it's nice because it will use the word left in there somewhere. It'll say a left-hand sum, or a left sum, or a left Riemann sum, or left height. But like the word left will be used. So it's pretty clear, well, come from the left. For the right side of each region, as the height of the rectangle. So the first rectangle would be, again, coming from the right. Now that first rectangle is an over approximation. Second rectangle from the right. That one's under. Third rectangle's a little bit over, but pretty close. Fourth rectangle, coming from the right. Definitely over. So for that one, we use all of those right-hand heights. Called a right Riemann sum. And again, when we want you to use a right Riemann sum, you'll know it because we use the word right. Right-hand sum, right Riemann sum, use the right height, right rectangles. You can call it 3 or 4 different things, but it'll all have the word right in there if they mean for you to come from the right. All right, third option. We can draw rectangles using the midpoint of each width. So, let's see. On that first width, the midpoint height is this height right there. So we make a rectangle with that height. Midpoint height. Same thing on the next rectangle, the midpoint height is right there. So we make a rectangle with that height. Third rectangle, find the midpoint, go up to the height. Fourth rectangle, again, go up to the height at the midpoint. So for that one, the heights we use were the midpoints of the rectangles. Again, for all those 3 options, all you're doing is adding up rectangles. And depending on the shape, maybe one of the estimates is better than the other. Kind of depends on the shape. And a few other factors. But we're not worried about how accurate it is right now. We're just getting an approximation. All right, lastly, we don't have to use rectangles at all. We could use trapezoids, which seems like it would be more accurate. I guess the trouble is the formula for a trapezoid is a little more complicated. But for a trapezoid, we're just going to connect the 2 heights. So there's my first trapezoid. Second trapezoid looks like a really good estimate of that region. Third trapezoid looks like a rectangle. That's okay. And the fourth trapezoid, another one that's a really good approximation of that area. So we're just adding up the trapezoid. Area of a rectangle, base times height. And for these 3, you would add up 4 rectangles. Base times height, plus base times height, plus base times height, plus base times height. Area of a trapezoid, a little more complicated. It's still base, but it's the average height. And you would do that 4 times, add them all up, and there's your approximation. Turn the page and things are going to get a little more complicated, but don't forget the fact that all we're doing today is adding up rectangles and adding up trapezoids. Alright, the area of a rectangle is base times height, or height times base. Each height is the function value at each x value. Each base is delta x. Maybe we should try to draw the picture again here. Or at least a little bit of a picture. So delta x is the base. And each height is f of some x value. Like x1, x2, x3, whatever, however many we want. So the base is an x value, height is a y value, or an f of x value. The area is the sum of all the areas of the rectangles. So now we introduce some fancy symbols, but remember, all we're doing is adding up the areas of a rectangle. Right? You remember what this symbol means back from pre-cal or algebra 2? Summation. That's a sum symbol, so that just says we're going to add up each of the rectangles. We're going to add up each height times each base. And each height is an f of x, and each base is a delta x. So we start to put fancy terminology on this, but again, all we're doing is adding the rectangles. So don't get lost in the fancy symbols. You're just adding the rectangles up. All right, then we make this significant jump, and this is where Riemann really gets credit, because if we let the number of rectangles go to infinity, let's back up a second. What would give us, kind of just answered this, what would give us a more accurate area of that under the curve? Yeah, more rectangles of smaller width. Right? Because then you wouldn't have these big gaps like there or there. If I had 100 rectangles in there, it'd be pretty accurate. Well, if you wanted it to be really accurate, if your rectangles went to infinity, you'd have exactly the right area. Now that's a calculus thing, because that's a limit as x goes to infinity. The summation, sigma, sign thing, turns into the symbol for integration. And again, this really is a elongated S. Here's my attempt to elongate an S. S for sum. So that antiderivative symbol that we've been calling antiderivative is also integration, which means sum. And if delta x gets really small, like you said, we're going to shrink that width of the rectangle, then delta x turns into dx. So f of x are all the heights, dx is all the widths, and so the area under the curve is, you add up all of the height times width from A to B. Now, we'll worry more about this later. Right now, we're going to approximate that with rectangles. So in the future, we'll talk about how antiderivatives relate to area, but for now, we're going to approximate the area. That equals the area. And we're going to approximate it, so not exactly equal to, we'll approximate it with rectangles or trapezoids. Okay, so we started with just add the rectangles or trapezoids. We get into some fancy notation stuff here. Now we come back to the end of it and we're like, yeah, but really all we're doing is adding up rectangles or trapezoids. So let's do some examples. Let f of x be a continuous function. Selected values of f of x are given in the table above. Estimate integral from 0 to 140 of f of x dx. So what that means is area under f of x from 0 to 140. So that's the fancy way of asking for the area. So estimate the area using a left Riemann sum, 5 subintervals, which you start looking at the table and you're like, oh, yeah, that's 1, 2, 3, 4, 5. So there's 6 points there, but 6 points make 5 intervals. Okay, so our area is going to equal integral 0 to 140 f of x dx is going to be approximated by, and now we'll add up the areas. So I don't really want to do a graph of this thing, I just want to think about this. This first rectangle, let's see if we can, well, I could almost, this first rectangle is 100 high, and how wide is that rectangle? 20. So if we're going to do base times height, the width is 20. The width of that rectangle is 20. Which height should I use, the 100 or the 90? If I want the left-hand sum, I should use the one on the left, the 100. I'm going to do lots of safe stops here because I don't want to do 20 times 100 and then add that. So we're just going to leave it as 20 times 100. The next one, let's see, we go from a height of 90 to a height of 80. Let's see, how wide, color coding my rectangles here, how wide is that rectangle? 30. So be careful, this one's not all 20s. This is not an equally subdivided rectangles, but that's all right. This one is 30 wide. And which height should I use? I mean, it helps if I cover them up like that. I want to use the left-hand height. It's like, well, that would be the one on the left, so let's use 90. 30 times 90. All right, from 50 to 70, the height goes from 80 to 80. How wide is that rectangle? What's the width? 20. And, well, I guess it doesn't matter which one we use on this one, but we should use the one on the left. 80. Well, that would have helped maybe, color code the height to go with the rectangles. Running out of colors here. Let's see, from 70 to 90, what's that width? Or excuse me, from 70 to 30. 70 to, keep answering my own question now. 30, thank you. Answer the question I'm trying to ask. From 70 to 100, the width is 30. And what height should I use for that triangle? Use the one on the left, that would be 80. And I think I'm out of colors, but hopefully you got the idea by now. 130 is way up there. So how wide is that last rectangle? 40. And which height should I use? 100. Oh, 90. I would need to use the heights. 40 times 90. So you look back and you see that we used all of the left-hand heights. That 130 we never used. But that's okay because that was a right-hand height and we were doing left-hand rectangles. With a calculator or with time, you could multiply those out and add them up, but we want to safe stop that. Like, leave that alone. Again, on the next test, there's a lot of free response because I don't want you to add them up. I want you to leave it like that because you're less likely to make a mistake if you just leave it like that. So it's easier for you. It's also easier for me to grade. I'm just looking at that you did base times height, base times height, base times height, and so on. Okay, a right Riemann sum. Oh, I did all those pretty pictures and drawings, and now I've got to use the other height. So the area is 0 to 140. Antiderivative of f of x dx. We're going to approximate that with a right Riemann sum. All right, why don't you try to fill that one in? So the first rectangle is 20 times 90. Autumn, what about the next rectangle? Okay, I'm going to stick with the base first just to be consistent, but yes, 30 times 80. Width of 30, height of 80 because we're using the right-hand height. Talk more, how about the third rectangle? 20 wide, 80 high. Good. Ambria, the fourth rectangle? 30 wide, 90 high. Justin, that last rectangle?
40 wide, 130 high.
40 times 130. Yep. And then you just leave it like that. You've added up the rectangles. If I or the grader want any more detail, well then we can grab a calculator and figure it out. Part C. Estimate using a trapezoidal sum. So the area is that integral 0 to 140, but we will approximate or estimate using trapezoids. Okay, a trapezoid is base times average height. So base of the first one is 20. Average height is, and some people, especially ones like this, some people are just going to look at that and be like, the average height is 95. And that's fine, especially for ones that are easy like this. I'm going to go ahead and write it out. 100 plus 90 over 2. Because if I get weird decimals, I don't want to be trying to actually figure the average. I'd rather just write it out like that. Oops. Plus for the next one. Let's pick on some people now. So that next rectangle, the second, not rectangle, trapezoid. Jameson, on the second trapezoid, how wide is it? 30. And how do I do the average height?
90 plus 80 divided by 2.
90 plus 80 over 2. Good. Austin's not with us, but Ava is. Ava, how about the third trapezoid? Yep. And that's another one where it's like, do I really need to write 80 plus 80 over 2? Isn't that obviously 80? Yes, it is, and if you see that, fine. But if you want to just keep the pattern of a trapezoid, then keep the pattern of a trapezoid. Luke, how about my fourth trapezoid? The 70 to 100 trapezoid?
Oh, yeah. 80 plus 90 divided by 2.
Yeah. Yes, but how wide is that trapezoid? Yeah. So 30 times 80 plus 90 over 2. And again, if you want to just in your head say that average is 85, that's obviously okay. Jace, how about my last trapezoid?
40 and 90 plus 2.
Yep. Add rectangles, add trapezoids. That's all we're doing today. All right, part D looks a little bit strange, maybe. That was quick. Part D. Given that the second derivative is greater than 0, second derivative is greater than 0, what does that mean? Second derivative is greater than 0. What does that mean? What does second derivative tell us? First derivative tells us slope. Second derivative tells us concavity. So if concavity is greater than 0, what does that mean? It means we're concave up. Is the approximation found in part C? Part C was the trapezoids. So are the trapezoids an overestimate or an underestimate? I don't know. Let's sketch it out and see. Like there's a whole bunch of different combinations of increasing and decreasing and concave up and concave down and overs and unders. But we don't memorize all those combinations. We draw out what's happening. So if I do something concave up, and it's best to like highly exaggerate the concavity and highly exaggerate or underestimate, well, I shouldn't use that word. Don't use very many trapezoids. Like you don't want this to be accurate. You want it to be highly inaccurate so that you can figure out if it's over or under. So let's say I only did like 3 trapezoids. So my trapezoids, just play connect the dots. So how do my trapezoids compare to the actual area? Are they over or under? They're over. And so all you would say is trapezoids on concave up give an over estimate. Some people are going to memorize that, but there's too many different combinations to memorize, and once you get one wrong, you miss them all. So, don't memorize that. Sketch out the situation, and then you can figure out if it's over or under. Okay, what haven't we done? Oh, we haven't done a midpoint. We definitely have time to do a midpoint. It might be all we have time for, but we have time for a midpoint. Okay, because there's something kind of different about this. Let h of t be a continuous function. Data's in the table above. Estimate 30 to 90, using a midpoint sum and 3 subintervals as designated in the table. So 3 subintervals, I should probably go 30 to 50, 50 to 70, 70 to 90. So I'm not going to have 5 intervals this time. I'm only going to have 3. So 30 to 90, h of t dt. That is the area, but we're going to approximate that using a midpoint. Okay, but it's still rectangles, so I'm still just doing base times height. Base of the first rectangle is 20. What height should I use? Here's the big thing. The 7, because that's the height in the middle.